All right, so now that we have finished talking about descriptive statistics, it's time to inch our way towards inferential statistics. And we can't begin to understand inferential statistics without some basic knowledge of probability theory. So today we're going to be talking about probability theory, and I'm going to introduce you to some basic probability distributions. Before I start talking too much about probability theory, though, I want to clarify some basic terminology. So there's some basic terms that I'm going to be using when I'm discussing probability theory that I just want to make sure that we're all on the same page for. So the first piece of information we need to understand is an event. An event is a basic bit of data, and that event can be anything. I am going to be talking about some very simplistic events. We're going to talk about flipping a head on a two-sided coin. I'm going to be talking about rolling a die, or even drawing a card out of a deck of cards. Those are very simplistic events, but the event can be any bit of data. It can be an anxiety score. It can be an IQ score. So any basic bit of data is going to be an event. But to help us understand, at least initially, to understand probability theory, I'm going to keep things pretty simplistic. And so we're going to be tossing a lot of coins and rolling a lot of die to kind of help us understand the basics of probability theory. But do understand that as we move into inferential statistics, we're going to use different events in inferential statistics. Another term that is important to understand is independence. And independence is that the occurrence or the non-occurrence of one event has no effect on the occurrence or the non-occurrence of another event. So much of probability theory actually assumes independence of event, that one event has no impact on another event. And so if you think about this, if I have a coin and I flip it one time and I get a head, does that head have any impact whatsoever on what I'm going to flip the second time I flip the coin? Or even if I had two coins and I flip them at the same time, does coin number one have any impact on what I'm going to get on coin number two? No, those two events happen to be completely independent. When I'm talking about things like rolling a die, flipping a coin, pulling a card out of a deck of cards, it's really easy to get independence of events. It makes a lot of sense in our mind. However, in social science research, it is important to acknowledge that we don't always have independence of events. Let me give you a quick example. So let's say that I want to see how people are likely to lean politically. So I call a random number. I just dial a random number and I say, excuse me, can you tell me, are you Republican, Democrat, or Independent? And they're going to tell me. And I hang up the phone and then I dial another number just completely randomly. Does the answer that we got from the first person have any impact on the answer that I'm about to get from the second person? No, right? Because they're two completely unrelated numbers. I dialed a random number, asked them, and now I'm dialing another random number and I'm going to ask this person. There's no reason to suspect at all that person number one has any impact on how the response I'm going to get from person number two. But social science research, though, is a little bit more complex. So if I dial a phone number at random, and I say, pardon me, are you married? And they say yes. I say, okay, good. Well, then will you tell me, are you Republican, Democrat, or Independent? And they tell me. And then I say, now may I talk to your spouse? And I'm about to ask the spouse whether or not they are Republican, Democrat, or Independent. Are they independent? Is that event independent? It's not going to be independent, because usually when people get married, they usually find people who, share similar values. So what person number one says is not completely independent from what person number two is going to say. There's a good reason to believe that those answers are going to be related in some way. So keep that in mind with social science research. We say that having this non-independence in these cases, especially I do a lot of developmental research, we're looking at one child and we'll ask mom and we'll ask dad to report on the same child. We don't have independence of those events in that case because they're both judging the same child. So that data is going to be a little bit correlated, and there are things that we can do to kind of compensate for that correlation in the data. So again, we have event, a basic bit of data. One of the big assumptions in probability theory is independence. Something else that's important to understand with probability theory is mutual exclusivity. And when I'm talking about something being mutually exclusive, it means that the occurrence of one event is going to preclude the occurrence of the other event. So once I have witnessed one event, it means the other event cannot happen. And so if I flip a coin, I have two outcomes, right? Heads or tails. If I flip the coin to heads, it cannot be tails. Heads is mutually exclusive with tails. So if I flip the coin and the coin comes up heads, it cannot come up tails. And don't tell me that there's a trick coin that's going to land on its side. That doesn't happen. So if I get heads, it precludes it from landing tails. If I roll a die and I get a 2, it precludes all other events. It precludes 1, 3, 4, 5, and 6. So mutually exclusive means that you can be only one in one event at a time. And then we can talk about an exhaustive set. So exhaustive means when a set of events includes all possible outcomes. So a set is said to be exhaustive when it includes all possible outcomes. With the things that we're talking about to kind of understand the basics of probability theory, this is really easy, right? An exhaustive set for flipping a coin is heads and tails. An exhaustive set for rolling a die is going to be 1, 2, 3, 4, 5, 6 if it's a 6-sided die. It gets a little bit more complicated when we talk about social science research because we don't sometimes even know if we have an exhaustive set. But if I talk about something being exhaustive, I wanted to make sure you understand what that's referring to. And then finally, when it comes to basic terminology, I'm going to talk a lot about sampling with replacement. What do I mean by sampling with replacement? It means that after each trial, all events are returned to their original state. So sampling with replacement means that after each trial, all events are returned to their original state. And in fact, this is actually one of the assumptions in most inferential statistics that we do. And it changes the probability. So let's pretend that I have a bag of 12 marbles, okay? So in my bag that I can't see through, I have a bag of 12 marbles. In that bag, I have 4 blue marbles, I have 4 red marbles, and I have 4 green marbles. So if I were to close my eyes and randomly draw a marble out of that bag, what is the probability that the marble I pick is going to be blue? Well, I had 12 total, right? And I had 4 that were blue. So it would be 4 out of 12 marbles are blue, which is really, it's a 33% chance that I'm going to draw a blue marble. Now I'm going to sample without replacement. So I pull out a marble. Oh, it's green. I'm going to set it aside. So how many marbles do I have left in the bag? Now I have 11 marbles left in the bag. 4 are still blue. So now it's 4 out of 11 marbles. So now my probability has changed. Instead of now having a 33% chance of drawing a blue marble out of the bag, now I have a 36% chance of drawing a blue marble out of the bag. So I'm going to close my eyes. I'm going to reach in again. Oh, it's a red marble. So I'm going to take that marble and I'm going to set it aside. Now how many marbles are left in the bag? Now there's only 10. So now I have a 4 in 10 chance of drawing a blue marble out of the bag. So now my probability is actually 40%. So when I'm sampling without replacement, it actually changes my probability. And so one of the assumptions for inferential statistics is actually sampling with replacement. The truth of the matter is we tend to not do that as long as our sample size is relatively small compared to our population. Then we don't worry about sampling with replacement, but do understand though that it is one of the assumptions, and if we are dealing with small data sets, then we really do need to emphasize the importance of sampling with replacement. So we have some basic terminology. Hopefully that was easy enough to wrap your mind around. I'm going to talk about a couple of important assumptions when it comes to probability. So we have a couple of assumptions worth mentioning. The first is that our probability values will always be greater than or less than 0 and less than or equal to 1. When we're calculating probabilities, it will always be between 0 and 1. If you calculate a probability and you get something that's negative, or if you calculate a probability and it's greater than 1, then you have miscalculated. Because what happens is that if there's an event it's impossible to occur, it cannot occur, then the probability of that event occurring is going to be 0. So if an event is impossible to occur, then my probability of that event is going to be 0. There is a 0% chance that that event can occur. And so if I were to have a bag of marbles that were all purple, what is the probability, if I have a bag of 20 marbles and all of the marbles are purple, what is the probability that I'm going to reach in there and I'm going to pull out a green marble? My probability is 0. It's not going to happen. It's impossible to occur. So my probability of pulling a green marble out of a bag of purple marbles would be 0. I have a 0% chance of that occurring. On the flip side, if an event is certain to occur, it is going to happen, my probability of that event would be 1.0. So if an event is certain to occur, then the probability of that event is going to be 1.0. I have a 100% chance that that event is going to occur. So in my bag of purple marbles, 20 purple marbles, the probability of pulling a purple marble is 100%. There's no other option. I am certain to pull a purple marble out of my bag of purple marbles. So my probability is always going to be between 0 and 1, between 0% chance and a 100% chance of that occurring. And keep in mind also that the sums of all of our probabilities assigned to all events, if I add them all up, is going to equal 1.0. So the sum of probabilities assigned to all events is going to equal 1.0. So we'll keep it really simple. So if I have a coin and it's two-sided, what is the probability of me flipping a head? 1 out of 2, 50%. What is the probability of me flipping a tail? 1 out of 2, or 50%, right? 50% plus 50%, 0.5 plus 0.5 is 1.0 or 100%. So I can add up all of my probabilities and it should always get to 100%. So those are two important assumptions. Probability will always be between 0 and 1, and if I add up all of the probabilities assigned to all the events, I should get to 1.0. So that is some basic information. When it comes to probability, there's actually no one agreed upon approach to probability. I am going to introduce you to two very widely accepted approaches to probability, but these are not the only approaches, but they are the ones that we are the most familiar with. The first one we've actually already been doing. That first approach to probability is called the analytic approach. And to calculate probability with the analytic approach, you've already been doing this. We were just doing this. For here, we take the probability of an event would equal the specific event over the total number of events. So if we want to keep it really simple, if you had a two-sided coin, right, your probability of flipping a head is 1 out of the 2 possibilities would be 50%. If we had a 6-sided die, the probability of rolling a 2 on a 6-sided die would be, well, there's 1, 2 on that 6-sided die, and how many total numbers are there on a 6-sided die? There's 6. So there's a 1 in 6 chance that when I roll that die, I'm going to get a 2. So that's 0.17, I think it's actually 0.1667, or about 16 or 17% that I'm going to roll a 2 on that 6-sided die. So we've already been doing that. You know how to do it. It's kind of implicit to you. We can actually also take a frequency distribution, and we can determine the probability of an event based on that frequency distribution. So I have all of these scores for some hypothetical test. I don't even know what test, but I have these scores for this hypothetical test along with the frequency that I see each one. This is a basic frequency distribution. You know how to draw these yourself. And so I can determine, so for example, let's say the probability of a score of 22. I can see how many people scored a 22, and 7 people scored 22 on this test. And then I can determine how many total people took this test by adding up all of the numbers under the frequency. So 3 plus 8 plus 12 plus 7 plus 6 plus 2 tells me how many total scores there are. And again, 7 of those total scores scored a 22. There were 38 scores total. So I can do some simple math. 7 divided by 38 is 0.18. So my p-value here is 0.18, or I have an 18% chance that if I were to draw somebody at random, that they scored a 22 on this test. I can do things that are a little bit trickier. So I can ask you to figure out what is the probability that somebody scored greater than or equal to 23 on this test. So now I want you guys to figure out what is the probability that somebody scored 23 or greater on this hypothetical test. So once again, you can use our frequency distribution here. You figure out how many people scored 23, 24, 25. You would add those up. And again, we still have 38 total scores. And if you did that in your calculator, which I hope you did, then you would see that 12 plus 8 plus 3, the scores of 23, 24, and 25, because we were looking for scores that were greater than or equal to 23, happened to be 23, divided by 38, so we have a p-value, a probability value of 0.61. And so we know that 61% of the people scored 23 or greater, or we could say that if I were to draw somebody from the sample at random, I would have a 61% chance that they had a 23 or greater. How about one more? I want you guys to try this on your own. What is the probability of a score less than 24? So I want you guys to figure out what is the probability of a score less than, not less than and equal to, but less than 24. So once again, you're going to add up all of those numbers less than 24, which would include the scores for 23, 22, 21, and 20. So it would be 12 plus 7 plus 6 plus 2. We divide by the total number of scores, which again was 38. And hopefully you guys did this in your calculators, and you figured out that it was about 0.71, a p-value of 0.71, or a 71% chance that if I were to draw somebody at random, that they would have scored 24 or less, or 71% of the people scored less than 24. So again, you're already familiar with the analytic approach to probability. You did it without even really thinking about it. This is something that's pretty implicit already for you. An alternative approach, which actually works hand in hand, it's going to be important later in the semester, is called the relative frequency approach to probability. So with a relative frequency approach to probability, it's a little bit different. So now we're talking about how our probability is equal to our observed frequency of specific events divided by the total number of observed repetitions. The observed frequency of a specific event divided by the total number of observed repetitions. So this particular approach to probability is based on this assumption that as the number of repetitions increases, you're going to approach your expected probability. And I'll give you some examples that will hopefully help you understand that a bit more. But it's basically saying it's the assumption that as the number of repetition increases, that we're going to approach that expected probability. And we actually have a name for that expected probability. That expected probability is called the limit. And so later in the semester, when we talk about inferential statistics, we're going to talk about central limits theorem. And central limits theorem is this idea that with a large number of repetitions, we're going to approach our expected probability. And so kind of think about it like this. As the number of repetitions increases, our probability is going to begin to stabilize. So our probability is going to stabilize as the number of repetitions increases. So if I were to give you a coin, a two-sided coin, one side's tails, one side is heads, and I were to ask you to flip the coin 10 times. Well, let's start off even smaller. If I were to ask you to flip the coin 2 times, what do you think the chances are that the first time you flip it, you get a head, and then the second time you get the tail, right? How many of you have ever flipped a coin and you're like, oh, it's heads, heads again, heads again, heads again. Oh my gosh, I'm never going to get a tail, right? This coin is broken. So when you're talking about a relatively small number of repetitions, we can see some wonky things happen with our probability. But if I only toss the coin twice, chances are not really that great that I'm going to get heads once and tails the next time. Or if I even had 2 coins, that I would get that. But as I get larger and larger numbers of repetitions, I'm going to begin to approach that expected probability. So again, a fair coin should come up heads 50% of the time. But anybody who's spent time just flipping a coin, seeing what will happen, will know that sometimes it doesn't work that way. So if I'm only flipping the coin twice, it's quite possible that neither of those times I'm going to get it to come up heads. So my relative frequency right there is going to be 0%. If I flip the coin 10 times, well, maybe now I get 4 out of the 10 flips is going to be ahead, but that's still not our expected probability as we determine through the analytic approach. It should be 50%. So the more I flip it, the more likely I am going to get closer to that actual 50% mark. So as you can see, as the number of repetitions increases, the probability of me getting exactly 50% is going to increase. So, and even here down at the bottom, if you look, if I flip the head 2,000 times, even if I only get 992 of those coin tosses are going to come up with heads, well, theoretically it should be 1,000 of them, but when you look at the rules of rounding, still that's 50%. So again, as the number of repetitions increases, we're going to get closer and closer to this expected probability. We call that expected probability the limit. This relative frequency approach is going to come in handy when we talk about central limits theorem a little bit later when we're talking about hypothesis testing. So I think we have our basics down. We have our two approaches down. Let's talk about our two laws. So let's talk about our two laws of probability. There's only two laws of probability and they're pretty easy to digest. The first law of probability is called the addition law. So we have the addition law and we have the multiplication law. And the addition law is saying, it's a little bit wordy, but it'll make sense after I explain it a little bit more. So the addition law says that if two or more events are mutually exclusive, because that's an assumption, mutual exclusivity is an assumption. So if two or more events are mutually exclusive, then the probability that one or another will occur is the sum of their separate probabilities. Okay, that's wordy, but it all needs to be in there. So if two or more events are mutually exclusive, because that's one of our big assumptions, then the probability that one or another will occur is the sum of their separate probabilities. We sometimes call this the either-or law. So the addition law is the either-or. I'm looking for either A or B to occur. And this is going to actually make it easier, right? So if I am looking at rolling a die, right? Sure, it's going to be hard to roll just one number, but if I can roll a 4 or a 5 or a 6, that is going to get easier. So rolling a 4 is going to be hard. I only have a 16-17% chance of rolling a 4. But if I can roll a 4 or a 5 or a 6, I can add those probabilities together to get my total probability. So here I'm looking at my individual probabilities of rolling a 4 or a 5 or a 6. Each one of those probabilities is going to be 1 out of 6. 1 out of 6 plus 1 out of 6 plus 1 out of 6 equals half. So I have a 50% chance of rolling one of those three numbers. Stop and kind of logically think about this. Again, by having this word or in there, it increases my possibilities, right? And so my probability should go up when I'm talking about or. To roll a 4 or a 5 or a 6 is actually making it easier for me to hit on one of the numbers that I'm looking for. So by adding those probabilities together, I'm actually increasing my probability. My other law is the multiplication law. And the multiplication law is also very wordy, but it all needs to be in there. So if two or more events are independent, another one of the assumptions here, then the probability that all of them will occur is the product of their separate probabilities. So if two or more events are independent, then the probability that all of them will occur is the product of their separate probabilities. And remember, a product is obtained when you multiply two numbers together. And so in this case, I think it's easier if I just, we also call this the both and law. So if we're looking at both A and B occurring, it's actually going to be a lot harder. So let's look at an example here. So if I had a die and I wanted to roll it 2 times, well, what is the probability of rolling a 6 on the first roll and then rolling a 5 on the second roll? This is actually going to be pretty hard, right? Because I only have a 17% chance of rolling a 6 on the first die to begin with. So now you're telling me I have to roll a 6 and I have to roll a 5. Well, it's hard enough just to get one of those numbers, but now I have to get both. So what's going to happen to my probability? It's going to go down. It's going to get more difficult. So I'm going to take my 1/6 times 1/6, which is 1 out of 36 now. So I only have a 3% chance of rolling a 6 and a 5. And if you really stop and think about this, my probability should go down. Again, it's hard enough for me just to roll one of those numbers that you're asking me to roll. But now I have to roll one of those numbers and then hold my breath and then hope that I roll the second number as well. So my probability is going to go down. In fact, to roll a 6 and then follow it up by rolling a 5, I only have a 3% chance of making that happen. So hopefully though, the laws of probability, the assumptions of probability, the terminology, the approaches, hopefully so far this isn't too bad. We're going to take it a little bit farther. Now that you have a basic sense of probability theory, we're going to discuss probability distributions, which are going to be central to inferential statistics. I'm only going to introduce you to 2 different types of probability distributions right now, and then next week we're going to up the ante and we're going to actually apply it to inferential statistics. But this week is all about just understanding the basics of probability and probability distributions. There are 2 different kinds of probability distributions that we can create, but either way it all starts with kind of like how our frequency polygon and our histogram started with the frequency distribution. We start our beautiful graphic probability distributions with a probability distribution, which means that we're going to list all of our events with a probability of each one occurring. So this is kind of like a frequency distribution where you list all of your events and then you tell what the frequency of each one is, but with a probability distribution, now we're going to list all of our events, and instead of having an F column, now we're going to have a P column. So we'll list all of our events, all the dependent variables, and then we're going to list the probability of each one of those events occurring. And there are 2 ways that we can create this probability distribution. The first way is the empirical probability distribution. The empirical probability distribution is based on experience. And so I have a couple examples of empirical probability distributions for you based on experience. So here we have a probability distribution for IQ scores, and then we have a probability distribution for my actual stats grades last time I taught this course. So we know from experience that only about 10% of the population has an IQ greater than 120, and we know from experience that only 10% of the population has an IQ less than 100 or less than 80, where the most of them fall in between 80 and 120. In fact, there's 80% of the population falls between 80 and 120. So this is telling me the proportion of people who have these IQs, but it's also telling me my probability. So if I were to go out into the population at large and I were to select somebody at random, I have an 80% chance that that person that I selected out there in this world at random, I have an 80% chance that their IQ is going to be somewhere between 80 and 120. I only have a 10% chance that that person that I just randomly select out there in this world at large has an IQ greater than 120. So these p-values are telling me my proportion of the population that fall into each of those categories, but it's also telling me the probability that I could select somebody at random and get them to fall within one of those particular categories. Down here at the bottom, I actually threw this up because I'm actually really proud of this. This is actually my distribution of stats grades last time I taught this course. Last time I taught the course, 25% of my students got an A, 35% of my students got a B, 30% of my students got a C, nobody got a D, and only 10% of my students last time I taught this specific course failed the class. And so those proportions look fantastic to you, right? Because that means that more than half of the class got an A or a B. And so as long as you guys do what they are doing, then there's no reason why you cannot do this if you follow my advice and take good notes and set up your data well and do extra practice calculations. There's no reason why you guys can't have a similar empirical probability distribution. But what this also means is that if I were to take my students from last semester and put them in a room and close my eyes and point to one of them, I have a 35% chance that the person that I pointed to got a B in the class. So it's telling me about the proportion of students that got these grades, but it's also telling me about my probability, if I were to select somebody at random, that I could get somebody who falls into one of these categories. So that's my empirical probability distribution. But the other kind of probability distribution is the theoretical probability distribution, and this is that probability distribution that's based on logic. You've already done this. You did it, you didn't even know what you were doing. And so the theoretical probability distribution is based on simple mathematics. So we've talked about these kinds of theoretical distributions already. So when we're talking about tossing a coin, right? Well, based on logic, there's a 50% chance that it's going to come up heads, there's a 50% chance that it's going to come up tails. We could talk the same thing with rolling the die. There are 6 options on a 6-sided die, 1 out of 6 for each of those. The probability is going to be 0.1667 or a 16.67% chance of rolling any one of those numbers. And so again, these are going to talk about proportions, but it also is going to tell me about my probability. So I have a 17% chance of rolling a die and getting a 4. So the probability distributions are a lot like a frequency distribution. Sometimes it's based on experience, empirical, and sometimes it's based on logic, theoretical. But let's graph them. Let's see what happens when we graph those probability distributions. When we're graphing those probability distributions, we actually have 2 different types of probability distributions that we can graph. We can start with a discrete probability distribution, which is going to graph the outcome of a discrete variable. Any discrete variable. Remember, a discrete variable is a variable that can take on a limited number of options. So we can graph a probability distribution for a discrete variable like gender, right? Male or female. We can do a probability distribution for hair color, blonde, brunette, redhead, and any of the other colors that we see anymore. And so we can graph these discrete variables, and they're going to be graphed with a bar graph. And so it's not a continuous variable anymore, so we can't call it a histogram. The bars are not going to be touching. But the nice thing is that when you're looking at this bar graph where the height of the bar equals our probability, the probability of an outcome between 2 values is really easy to determine because we can simply add the probabilities of all those bar heights, of all the inclusive outcomes. And so if we want to look at this graphically, so the probability of an outcome between 2 variables is found by adding the probabilities of all inclusive outcomes. And looking at this graphically, we can see now we still have our dependent variable across the bottom, what we are measuring. In this case, we're looking at the outcome of tossing 2 fair dice. So we have 2 6-sided die that we're going to toss. And over along the side, along the y-axis, instead of having frequencies now, we have probabilities, but it looks a little bit more like that histogram that we're used to seeing. Again, because this is a discrete variable and not a continuous variable, the bars are separated, they're not touching because this is not a continuous variable. And if we want to determine the probability of rolling, of rolling a 3, right? We can go to the 3 and we can look up and we'd say, that looks like it's maybe 0.057, right? So we kind of make some guesstimates based on this, but if we go to the 3 and we go up to the bar height, it's somewhere between 0.04 and 0.06, so I'd say 0.057 is my best guess. But we can also then look at the probability of rolling somewhere between a 3 and a 6. And so then we would look at this bar height, 0.057, we'd look at the 4, which would be maybe 0.081, and then the 5, which is maybe 0.11 something in there. And so, or it'll be 0.112. And so we could just simply add up those bar heights, and that's going to tell us the probability between these 2 outcomes. When we have a bar graph, it's a little bit easier. Again, we're just looking at bar height and then we're adding up those numbers. It gets a little bit more complicated with our other type of variable. Remember way back when we talked about the difference between discrete and continuous variable. Oh, I'm going to come back to that one in class. Don't worry about that slide. Then we have the continuous variable. So a discrete probability distribution graphs the outcome of a discrete variable, but a continuous probability distribution is going to graph the outcome of any continuous variable. If you can figure out a continuous variable, you can graph it. This is not going to be a bar graph though. This is going to be a frequency polygon. So instead of using a bar graph, now we're going to use a frequency polygon because we're dealing with a continuous variable. But because of that, it gets a little bit trickier. And so now we cannot just look at bar height. Now the probability of an outcome between two values is the proportion of area between those two values in the graphed distribution. So I'll repeat that. The probability of an outcome between two values now is the proportion of the area between the two values in the graphed distribution. This gets a little bit trickier. So if we look at this graphically, so once again, we still have a similar looking frequency polygon than we had before with our dependent variable down here at the bottom and our probability over here on the side rather than our frequency. We have a beautiful, nice mesocurtic curve. But now to figure out what is the value between people who score 7 and 9, I cannot just look at bar height to figure this out. Instead, what I have to do is figure out what percentage of the curve is shaded in green, or what proportion of the curve is shaded in green. And if I can figure out what this proportion is, so here under the curve we have 100%, right? But I just want to look at this little piece right here. If I can figure out what percentage of that curve that is, then that is going to tell me my probability. And so this is a little bit trickier now that we have a continuous probability distribution, now that we have a continuous variable, but it's actually not that difficult. There's a simple, really simple calculation and a table that is going to help us determine what that proportion is going to be. That's what we're going to focus on next week, but before I send you off, there's a couple of things that I want to make sure are really clear before we leave, because this is going to be kind of the basis for next week, when we actually will figure out what percentage of the curve is shaded in this continuous probability distribution. So a couple of important notes about those continuous probability distributions to make next week easier. First of all, the area under the curve is 100%. So if you look at that nice, beautiful bell-shaped curve, underneath the curve is 100%. And our job is to figure out the proportion that is shaded. So under the curve is 100%, which is the total probabilities of all possible outcomes. So the area under the curve is 100% because that is the total probability of all of our possible outcomes. What we're looking for, though, is that shaded area. So we have to figure out what proportion of the curve has been shaded. And that proportion of the area that is shaded is equivalent to the proportion of the observation that we're looking for. And keep in mind, I'm going to use these words, these P words interchangeably, because a proportion is a probability. If I can figure out what proportion of the curve is shaded, then I can tell you the probability of that event. So a proportion is a probability, and a probability, here, let me go back to here. So the proportion of the area within any section of the graph is going to equal the probability of an outcome within that section. So a proportion is a probability, so that the proportion of an area within any section of the graph is going to be equal to the probability of an outcome within that section. And that probability is a percentage. So if I figure out that 22% of my graph has been shaded, then I have a p-value, a probability value of 0.22. So probability equals proportion equals percentage equals p-value. All these different p words are all interchangeable because a proportion equals a percentage equals a probability equals a p-value. All of those things are referring to the same thing. And we can figure out that proportion or that percentage of the curve that is shaded or a probability of that event occurring between those two points or my p-value for those events with a simple calculation in a table. And that's what we're going to be doing next week, is we're actually going to break down this continuous probability distribution so that we can find the area that is shaded, so we can find the proportion of the curve that is shaded. Because if we can find that proportion of the curve that is shaded, what percentage of the curve that is shaded, then that tells us what our probability is of that event. So that is it for probability theory. It is the backbone of inferential statistics, because next week we're going to talk about that standard normal curve, which will then allow us to find the probabilities under the curve.